Final quantitative project for optical lens thickness parameters. The topic I have chosen for my quantitative projects is the optical lens thickness parameters as it relates to the quality of productions expressed by the given dataset. Of the two provided datasets, I chose the lens thickness set because of my hobby of photography and media production. I have prior knowledge and experience as a customer and consumer of optical lenses for video camera, projector, and photo camera lenses. Quality as it pertains to the lens thickness parameters for optical lenses means that the product is produced with consistency and reliability with as little variation as possible. Also, quality means that the project is produced to specifications that satisfies the customer's demands and fulfills their needs. The data for optical lens thickness parameters collection was given. A quality engineer at an automotive parts plant monitors the thickness of lenses. The engineer measures a shift's worth of production using subgroups of 5. The specification limits for the lens: target equals 0.405 inches, LSL equals 0.395 inches, and USL equals 0.415 inches. The quality characteristics of this dataset provided are variables of the individual product attributes. The appropriate control chart for this process output is the XRR charts. This type of control chart is used to monitor the mean and the variation of the process when continuous data and subgroups of 8 or less, in this instance 5, are given. If a product is to meet or exceed customer expectations, generally it should be produced by a process that is stable or repeatable. More precisely, the process must be capable of operating with little variability around the target or nominal dimensions of the product's quality characteristics. Using the control chart, we can express the process stability variance from one instance to the next. It can be concluded from this data that the process remains stable after 1,000 instances to stay within the customer's specification limits of target of 0.405 inches with an LSL of 0.395 inches and USL of 0.415 inches. The data for optical lens thickness parameters collection was given. A quality engineer at an automotive parts manufacturer is qualifying a model of a new camera lenses for a customer. The engineer measures a lot of 250 lenses using subgroups of 5. The same specification from before are used to generate the tolerance interval plots for sample, with the added specs of mean equal to 0.405 and standard deviation equal to 0.003. From these values, a process capability ratio is calculated to be 1.0194. Present is a tolerance interval plot to determine if this lens meets the customer's quality expectations. The production process is able to deliver lenses that meet the customer's demands with 96.9% confidence. The projected output outside of the specification limits is 3.1%. From the data provided, it can be concluded that the process is stable. The products meet the customer's specifications. The mean of the samples is almost equal to the target. The standard deviation is low and the lenses produced stay within the USL and LSL. The objectives of an experimental design are to obtain the maximum amount of information using a minimum amount of resources, determine which factors shift the average response, which shift the variability and which have no effect, build empirical models relating the response of interest to the input factors, find factor settings that optimize the response and minimize the cost, and validate or confirm results. Taguchi designs use orthogonal arrays, which estimate the effects of factors on the response mean and variation. An orthogonal array means the design is balanced so that factor levels are weighted equally. Because of this, each factor can be assessed independently of all the other factors, so the effect of one factor does not affect the estimation of a different factor. This can reduce the time and cost associated with the experiment when fractionated designs are used. There are 3 noise levels in this example: ambient temperature, moisture content, and percent regrind. There are 2 levels of the 7 controllable factors. Most controllable factors originating from the machine which is used to produce the product. Noise factors primarily originate from the product's materials and environment of production. For the acceptance sampling example, the following information was provided pertaining to the dataset. A camera manufacturer receives shipments of 3,600 lenses several times a week. The quality team takes samples of 259 lenses from each shipment and measures the thickness to determine whether to accept or reject the entire lot of lenses. A defective lens is one that is thicker than 0.415 inch, which is the upper specification limit, or thinner than 0.395 inch, which is the lower specification limit. From the lot of 3,600 lenses, the manufacturer and its supplier agree to set the acceptable quality level, AQL, to 100 defectives per million and the rejectable quality level, RQL, to 600 defectives per million. Producer's risk of 0.05 alpha and the consumer's risk of 0.10 beta. Acceptance sampling plan needs to be generated for the random selection and inspect 259 of the 3,600 lenses. Accept lot if standard deviation less than or equal to MST, ZLSL greater than or equal to K and ZUSL greater than or equal to K, otherwise reject. Given the following values of sample size 259, critical distance or K value 3.449, maximum standard deviation 0.0028, standard deviation 0.0469, mean 0.403, we can then calculate the ZLSL and ZUSL. Standard deviation is not less than or equal to the MSD, ZLSL is not greater or equal to K, ZUSL is not greater than or equal to K. Using the acceptance sampling plan, it can be determined the sample lot should be rejected.